Transformers are the unsung heroes of our electrical grid. They take the extremely high voltages needed for efficient long-distance power transmission and step them down to the safe, usable levels our homes require. But how does this seemingly magical box actually work? And more importantly, what are its real-world limitations? At its heart, a transformer is just two coils of wire, the primary and the secondary, linked by a magnetic core usually made of iron. The magic comes from a principle discovered by Michael Faraday, Faraday's law of induction. When we apply an alternating voltage, V1, to the primary coil, it drives an alternating current. This current creates a changing magnetic field, or flux, within the core. This same changing flux then passes through the secondary coil, inducing a new voltage, V2, across its terminals. The key insight is that the induced voltage in each coil is proportional to the number of turns, N, in that coil. Since the same flux links both, the ratio of the voltages is simply the ratio of the number of turns. This is the ideal transformer equation. But of course, no transformer is perfect. The real world introduces losses. First, the copper wire used for the coils has electrical resistance. As current flows, some energy is lost as heat. We can model this by placing a resistor, R1, in series with the primary winding and R2 in series with the secondary. Next, not all of the magnetic flux created by the primary actually makes it to the secondary. Some of it leaks out into the surrounding air. This leakage flux creates a back voltage, which is the defining behavior of an inductor. So, we add leakage inductors, or reactances XL1 and XL2, in series. Even with no load connected, the transformer still needs to draw a small current from the source just to build up that main magnetic flux. This is called the magnetizing current. We model this by adding a magnetizing reactance, XM, in parallel with the primary. Finally, rapidly changing the magnetic field in the iron core isn't free. It generates heat through hysteresis and eddy currents. This continuous power loss is modeled by another resistor, RC, in parallel with the magnetizing reactance. This model is accurate but cumbersome because of that ideal transformer in the middle. We're dealing with two different voltage levels. To simplify, we can refer components from the secondary side over to the primary side. It's like converting currency using an exchange rate. The exchange rate is the turns ratio, A. If we rearrange the equations, we find something remarkable. The referred impedance is equal to the original secondary impedance multiplied by the turns ratio squared. This A squared rule is our key. And with that, the ideal transformer vanishes. We are left with a standard electrical circuit entirely on the primary side. We can even combine the series resistors and reactances into equivalents. This is the exact equivalent circuit of a transformer.